with the alpha particle. This is why we have this relation. Yeah? Using this relation, then we can replace in the kinetical energy, where you can remember that the kinetical energy is related with the momentum, like momentum square over 2 times the mass. Yeah? Then we can find how much is the corresponding contribution to the kinetical energy to the alpha particle. That in this case is going to be K minus KD. Then we had this relation. You do the substitution, and then we find the energy for the alpha particle. Okay, and then you can just play with the numbers because we know the mass of the daughter, the parents, and then we found it. Okay, now let's go to the beta decay. Okay, the beta decay, what do you think that is the beta decay? Exactly. And how this happened? Okay, well, this was good. In this case also we had a decay. We had actually something really interesting, that is that the neutrons are going to turn into protons. The first time that I listened to that, I was like amazed, like, okay, now we have the neutrons that are going to become like protons. It's kind of how this happened. Yeah? Then this is actually happen, but to happen this need to be something extra, need to be an emission of something, because for conservation of energy, we cannot just say that we can transform neutrons in protons. Okay, then how did it happen? Again, we had a really big chemical that had a lot of protons and neutrons. It's unstable. This instability is always gonna try to look for a more stable state. Then, in this look of stability, then the neutrons are gonna be easy to escape. But when this happens, then this one is going to emit some electrons, but it's not just electron, it's an electron that is going super fast. This is why the beta, that is actually an electron, is different to the normal electron. It's an electron that is faster. This is the difference. Then this is the beta minus. And in this case, then we have that the neutron is going to be transformed in proton. Then we're going to have that we lost one neutron, but we win one proton. Okay? And now, oh, sorry. Okay, I just like to make sure that was clear. Was clear? Okay. Now the second thing that we can have is that the proton is going to turn into neutron. That is called the beta plus. Then in this case, it's going to happen the opposite. We are not going to lose a neutron. We are going to lose a proton, but this proton is going to turn into a neutron. But as I tell you before, for conservation of energy, something is going to happen. Then we are going to have an emission of a positron. Who can tell me, who remember what is a positron? Yeah, it's an electron with, but the charge is positive, exactly. But then it's going to be an electron with positive charge that is going to move super faster. Yeah, and this positron also has the same spin that is half and has exactly the same properties that the electron, but the only difference is that the charge is positive. Okay, then after that, then, as I tell you before, it happened because we had an unstable nucleus that like to move closer to the line to the stability. Then in this kind, we can lose a neutron. For example, in the beta minus decay, we lost one neutron, but we won one proton. Then we're going to have something similar with the thing that we observe here. It's initially, remember that this number is related with the number of protons that we have. Yeah? Then, if we lost one neutron, but we won one proton, then we're going to see that this number is going to increase. And additionally, we are going to have the extra particle that is the electron. But it's the fast electron that is the beta particle. Okay. Additionally, then we are going to see in more detail what is happening inside. Because actually not only we had the electron and the positron, but also in this kind of decay we can have also antineutrino a neutrino. Who remember what is the neutrino and antineutrino? It's like a particle that doesn't have any charge. Then it's going to be an extra energy that is going to be added. Okay? Okay, now we have then that the kinetical energy also is going to change. And then we had a weak interaction now inside. And we are going to have this relation here, as you see. For the beta minus the k, then we have that we are going to transfer one neutron into a proton plus the electron high energy with the high speed that is going to be the beta minus plus we had then the neutrino, and then we had also, for example, this kind of decay where we are going to transfer the carbon that I told you before here. Oh, sorry. I moved too much. Okay, we're going to have the carbon that is, we increase the number of protons, then we're going to have one more. And then we have our balance of energy. And then in general, it's going to be valid that we are going to increase the number of protons, and then we're going to have these two extra components in the balance of mass in our system. And also for the conservation of the energy, then we are going to have the mass, and we are going to have the two components that come for the parents and for the daughter. Okay, and in the beta plus, that is for the positron, we are going to have something similar, but the difference is that we are going to lose one proton. Yeah, in the other case we won, and here we are going to lose, but then again we have the conservation of energy, then we are going to have this relation. Okay, now we are going to go into the electron capture. Okay, until now we are talking about losing all the time. Then we lost proton, we lost neutron, and then we are going into a state that has less neutrons or we have less protons. Yeah? But now we are going to talk about electron capture. What do you think that is electron capture? Exactly. In this case, we like to look for stability by adding electron in the system. Yeah, but then look, it's kind of interesting because the thing is we like that the electron go inside and be part of the nucleus. This means it's going to combine with the proton and it's going to form a neutron and neutrino. Then in this kind, for example, is we had carbon, that this kind of thing happened, for example, in the carbon. Then one of the electrons is going to be absorbing because we're looking for stability. And then, for example, in this case, we are going to transfer our electron into a neutron and proton, and then we're going to have a plus extra neutrino. Then how is this happen? In this case, then we are going to lose one proton, and for the extra energy, then we are going to want a neutrino. Yeah, then we are going to have that. The reaction is going to be proton plus the electron is going to be a neutron plus a neutrino. This means that this new electron is going to give place plus the proton to a new neutron plus neutrino. This is the idea. Actually, it's interesting to see how the nature trying to look at stability is using different results. Sometimes it's taking out neutrons, protons, or other times, depending on how it's the system and how everything can be more stable, can be trying to capture some of the electrons and had some extra energy, because if you see all the time we had some extra energy, and then we're going to have different components that are going to be more stable. Then it's kind of really nice. Okay, then now we have another kind of decay that is the gamma decay. In this case, I don't know if, how do you think that is going to be the gamma decay? In the other case, I told about how you can lose or win something. Like you lose neutron, you can go proton, and then you are sending some energy. In the case of the electron capture, that you are taking one electron, and then plus the proton, that you are going to have a neutron plus a neutrino. Now what happened with the gamma decay? What do you think that is going to be in this case? Okay, happen that the gamma decay is a little different, because in this case, the atom doesn't like to change to a new one. It's kind of like themselves and say, okay, but then it has too much energy. Then it's kind of an atom that has too much energy, then it's beginning to emit light, but doesn't change to a new state. In the other case, for example, we had that uranium was going to the thorium. In this case, no, we had that continuum be the same, but it's sending light. But it's super stronger emission. Is you see here is in the order of the mega electron volt. This means that it's not just the light that you see, but it's going to be super stronger. Stronger somehow that can burn your skin, can kill yourself, then it's kind of dangerous. Then in this case, this emission of energy is going to be decayed, but you are going to preserve the same atom, as you can see here. Then it's going to just go to a small state. This means you are in a high, really exciting state, and then you're going to begin to lose the energy. In the process of losing the energy, you are going to a more stable state, but continue to be exactly the same component. Then here, for example, we can observe the decay that we had, for example, 5.818 mega electron volts. Then we're going to begin to lose. Depend where you like to go. If you like to go for the closer state, you can lose like 0.38% of the energy, then you are going to 5.667, or you can jump to a more stable and lower energy, then you are going to have 0.07 mega electron volts. Or you can go to the state that is more stable, then you are going to have loss of 77% of the energy. Okay? Then in the gamma decay, then we had that as atom is going to be exactly the same, but we have the emission of the gamma ray that is going to be related with the frequency and the Planck constant, and then we had that this is going to depend on the difference between the energy of the different states inside the atom. Then in this case, we had exactly the same component, but the only thing that is changed, this is how it's represented when it's in a really high state, but it's the same. And after that, we lost this energy, and then we had the emission of the gamma particle, and then we're going to have transition between this state, but we had exactly the same component. Okay, then in this, the gamma ray are normally emitting soon after the nucleus is created in the excited state. And then sometimes then a selection route prohibits a certain transition, and the excited state may live for a long time. When this happened, then we had kind of metastable state. Actually, we can observe this kind of behavior. Do you remember this kind of slide that sometimes they put in the children room that they stay for some time and begin to lose the light? That is fluorescent.
It's phosphorescence, actually.
Phosphorescent, yeah. Then this thing is, for example, in this state with the light, obviously it's not gamma ray, but it's kind of the analogy, no? When you have this energy, because you are not charging, you put this thing in a charger, you take it out, but when you take it out, you still have the light and stay for a long time. Then it's gonna go slow, but it's not changed, the same thing. Then it's gonna be just preserving the light, and slowly, it's gonna be losing the energy. Then it's kind of the analogy, and that state is a metastable state, because it's not a stable state because it's not gonna be there. It's not unstable because it's not changed so quickly. It's metastable because it's gonna stay for some time, it's gonna relax, stay, and then go and disappear. Then is that. Also, then we had in this case, when we are talking about the gamma decay, then we call them isomer state. That also, as we can see here, denoted by a small m for metastable. That they are metastable, but they are isomer state. And then he has, here we had some examples. For example, the 210. Here, the m is going to represent that is in a metastable state. Then it's going to stay some time. And then after that is going to the real stable state. And then, for example, in some cases, doesn't emit the gamma decay because it's a large spin different transition. When it's too large, as I say, in the other case, then it's going to be just in the metastable state for some time, and because also it's forbade to cruise quickly to the other, because as I said before, to cruise to the other state need too much energy, but doesn't have this energy. Then it's kind of stay in this state as long as they can stay. Okay, here for example, we had some examples of unstable nucleus that we can find in nature that exceed a natural radioactivity. Yeah, for example, rubidium, then we have the potassium. They can have some transition and then they are going to be emitting radiation. But naturally occur radioactivity in nuclears. And we had others that